Thank you. So, as he mentioned, my name is Greg Arundale. I work for Rockwell Collins. I've been in the avionics industry for over 30 years, so some of you may not be even that old. So, being that I've been in the industry that long doesn't mean that I'm an expert on everything, but I've spent a lot of time with multicore processing and have a lot of background and knowledge about the things that have been happening and some opinions, at least, on what needs to happen. And that's blank. There we go. So this is just an outline of kind of the structure of the presentation. As was mentioned this morning, within this industry, there tends to be difficulty of getting data out for public release. So these slides don't have a lot of deep detail, but the intent is that it at least gives me something that I can use to talk about things in a little bit deeper method. But most of this information is fairly generic, and a lot of you may already know it, but we will hopefully be able to use this to have a little bit of time at the end to ask questions and have a little bit more of a conversation. So just as an introduction, multicore processors are having more and more performance, and most industries have adopted multicore processors sooner than what avionics industry has. Consumer, obviously, computing environments. Automotive is really starting to get into multicore processing within their environment as well. Of course, telecom and networking all have a pretty good history with multicore processing. Avionics has been a lot slower to adopt, but we have, over the last decade, spent a lot of time getting to the point where we can get multicore processors into certified systems. So the main questions are, what are the problems that multicore processors give to the avionics industry? Can we utilize things from other industries to help bring those through to a certification authority and to be certified onto safety critical applications, and what things we need to be aware of as we move through that process. This slide kind of gives an overview of the evolution of avionics systems over the years. Back maybe 60, 70 years ago, everything was independent. You got a box that did every function. Those things started to be integrated into federated systems, bringing things together so that you had fewer devices on the aircraft. Federated systems were continued up through into the 80s probably, at which point 80s and 90s got in more towards moving towards the integrated avionics. Integrated avionics became much more prevalent mid-90s to the last decade. That's where you have a cabinet-based architecture, reusable processing elements, for instance, and software running on each of the processing elements, which change the functionality within each circuit card, depending upon the applications that are necessary. The last diagram, these diagrams came out of something that was published 15, 20 years ago probably. And that last diagram is a little bit of a disconnect from what needs to be understood for advanced architectures. But should be an arrow on there. Yeah, an arrow that shows the increasing complexity. The last diagram really has elements that were being done even prior to integrated avionics. We did a system back at Rockwell Collins, late 90s, that was a lot like that last diagram. But the concept there is that more advanced avionics are moving towards systems which are trying to utilize the increasing amount of data that there is available to create systems that are more cost effective and provide better use for the pilots within the aircraft. Some of the things that would be under that area would include augmented decision systems, synthetic vision, which is in a number of aircraft now, and eventually, and I don't know whether this is 10 years from now, 20 years, 50 years from now, but there is early work being done for autonomous flight rules. Eventually, we believe that there will be a change to autonomous flight rules within the avionics industry. NASA has already funded efforts to look into this and has looked at what research needs to happen to make that happen. But it is a ways off. There's a lot of things that need to happen before we get there. As this progression has happened, there's a lot more processing capabilities that are needed, partially because you're taking software that was running in systems back in the 70s. The applications don't increase, but the available processing capabilities are increasing. Therefore, you've moved from multiple processors onto single processors and used partitioned operating systems to allow multiple applications to run, and separating them by time, both time and space. And there was some discussion of time and space partitioning earlier in the automotive discussion. So this is something that we have been doing for years, that partitioning environment, keeping that brick wall between the different applications to prevent one application from interfering with another application's memory and I/O. These things, of course, as we get into multi-core, become more difficult and more challenging. So again, more from avionics background. Today, most things are integrated systems. There's very few that are considered federated anymore. We are using a lot of partitioned operating systems to implement those systems, and instead of the case where in the early days every sensor, every device had its dedicated connection to a system that then processed all that information and then sent its output to the next stage, etc. A lot of wires go into that type of a system. A lot of that has collapsed into a network-based infrastructure, and using either directly out of each device networked interface, or running those into data concentrators where everything gets put onto a data bus, and that data is shared amongst multiple devices within the system, so that you can have redundancy, processing the data in different places, voting that data, and providing a much safer environment than you would otherwise. So what challenges does the avionics industry have in looking at multiprocessors in general, not even multi-core processors? Because this is safety critical equipment, there's a lot of issues that we have to deal with. We have to have devices that will run in an environment which is not normal for processors you'd use in a PC or in the phone you carry around in your pocket. But we have to be able to operate over much wider temperature constraints, power constraints. We have to worry about single event upsets, which are more prevalent at altitude. There's product longevity. We design something, we have to be able to support that for 20, 30, maybe even 50 years into the future. We have a very stringent certification process. We have a lot of information we have to provide to the certification authorities to get things to be accepted, to be able to be used on an avionics application. Determinism is a cornerstone for a lot of what needs to happen. When we do a design, we have to know that the output from a process is going to be the same, given the same inputs every time it's run. And modern processors have some issues that make that a little more challenging to obtain. And there's always increasing performance demands, not necessarily because the functions are harder to do, but because with more processing capabilities, people want more things to be put into the systems. And again, I mentioned synthetic vision. That was one of the things that brought a lot of additional processing needs into the systems and drastically increased the amount of processing needed to be able to provide the augmented data in front of the pilot. So all of these concerns get exacerbated by multi-core processors. Multi-core processors, we don't have as much visibility into what is happening as we did when we had discrete processors with data buses between them. We could monitor things. We could have external devices validating the data flow and the output from the devices. But all that stuff is embedded now into a system on a chip, and it's difficult to be able to see what's going on. So with the higher integration of processing capability into single devices, that makes our job a lot more difficult. So our challenge currently is for our industry to take advantage of investments from other industries. Especially today, the work going on in the automotive industry, we're hoping that we can leverage a lot of that, because whereas device vendors have a reluctance to spend time with someone in the avionics industry because of the low volume relative of what they would sell to us, they will work a lot more with the avionics or the automotive guys, because if you're building millions of cars, you're going to use a lot more parts than you are when you're building hundreds of aircraft. This slide, I think that most of you have seen something along these lines before, but this talks about why multi-core processors. A lot of the information that you can kind of glean from this slide has to do with if most of you have heard of Moore's Law. Moore's Law stated that originally that every year the number of transistors on a device would double, and that got morphed into saying that every 18 months performance was going to double. To increase performance within a processor, mostly that was done by increasing clock speed and numbers of transistors. But at a certain point, it began to slow down because clock speeds could not increase faster, and numbers of transistors didn't help when you already had every transistor you needed for a processor. So you could make it smaller, you could make it faster, but the speeds were not going up as nearly as quickly. So this chart shows how, as that from the hardware infrastructure standpoint started to change, they started increasing numbers of the pipelining architectures to continue the Moore's Law curve, but pipelining became less able to meet that need. So a gap started to develop, and that gap has now is being filled through putting multiple processors on a die rather than a single processor, and splitting applications across more than one core, or those other processors may actually be offload engines or graphical engines or some engine that's designed specifically for a task. And in this way, the increase in performance has continued to go up. So within the avionics industry, there are roadblocks to use of multi-core processors. This slide has, from its original state, has been changed a little bit more to state what's being done in each case. So there was, years ago, there was a lack of certification guidelines. How are we supposed to certify these devices? Everybody was worried about it, but nobody was telling us how we needed to go about certification. CAS 32A and the EASA's CRE has come out and provided that guidance. But that guidance is still based upon requirements stated in DO 254, DO 178, ARP 4754, etc. So the requirements are still there, and it's a matter of how do you meet those. At least we now have these guidance documents which give us a view as to how we can meet the intent for the certification authorities. And that's gone a long way within the last couple of years of providing the industry with methods, with knowledge about what things the authorities are going to require in order for us to get things through a certification process. Another issue that has cropped up is the fact that we don't have access to artifacts for these highly complex devices. It was not as big of an issue before because the devices were able to be monitored outside of the parts, and so we were able to design without having to have those artifacts in place. But as the devices have become more and more complex and more systems on a chip type of devices, we have had this gap of knowledge about what is going on inside the device. We have been able to work through some of that with an organization called Multicore for Avionics, MCFA. That started in 2010. I was one of the people who helped to found that organization, and a number of people within the avionics industry are involved with that, working with certain device vendors to provide data that we need to be able to design safe systems using their processing infrastructures. And of course the fact that determinism is a major issue within safety critical applications. Every time that we look at a device that has more and more performance, it's got less and less determinism. So we end up having to turn off features that provide that additional performance in order to keep determinism at a level that is acceptable for our certification authorities. One case listed here is the multi-threaded architectures that typically is not used for design assurance level A applications. And the reason why is that within a processor, if it's got dual or multi-threaded capabilities, those threads use common resources inside the processor. Therefore, because of the reuse of common resources, it's less deterministic. You could have a case where the same set of instructions can run through the device one time, and the next time it goes through, it could take more or less time, and therefore your determinism has gotten blown out of the water. So typically, we turn off multi-threaded capability. That decreases your performance drastically. Almost twice if you've got a dual core or dual threaded processor. Now, if it's a multi-threaded processor, it can be more.
Hyper-threading, or you
yeah. Hyper-threading, dual threading is just a simple form of hyper-threading. Yeah. And just a little more on the issues with multi-cores, again on performance. As cores began to be moved into a multi-core environment, in many cases they would take out features to get more cores to fit. That would mean that each core would often have lower performance than the single core equivalent device that it came from. And resource conflicts also slow the performance. So, and you also have hypervisors, which you need to have within the device to keep your partitioning between the different applications that are running on that core. All of these have effects on performance. Debug is difficult. You don't have access to see everything going on inside the device and in between the processors. So new methods are needed and new tools to help us to do that to do that debug. Again, on determinism, there are conflicts that occur with shared resources, and that causes problems with your determinism. And certification authorities tend to view multicore with a lot of apprehension. They don't like to stick their neck out to be the first one to say yes on a multi-core design. In fact, I just finished a proposal with an unnamed company, not doing a civil cert, but it would be a mill cert, who absolutely would not allow us to use multi-core processors. And you really can't get anything but multi-core processors anymore. So our proposal ended up being a multi-core processor with all but one core turned off, which means we have to put multiple processors in rather than a single processor. Increases the cost, increases the card count, increases the power, because they know that they don't want to trust it because they can't get it certified through their certification authorities. That is a common issue, and that's something that we are, as a company, working through, and as an industry, we're working through to try to provide ways to get around that. And Louis Shaw and people at the University of Illinois have done a lot to help us to have methods that we can do that. There's going to be a single core equivalence discussion after this, I believe, and there are some solutions within there that I think that we can leverage. Some background on MCFA. Again, as I mentioned, it was started in 2010. It's an ad hoc working group. It's supported by the silicon vendors, which we are targeting for use of their devices. Freescale was the first to do this, and now there are a handful of others that also support the MCFA working group.
Can you say who those are? I mean, is it like ARM and everything?
I can tell you that directly neither of those.
Neither of those?
Neither of those directly. ARM is not a silicon vendor.
Okay.
But the only reason I can say Freescale is that was publicly released years ago. The other companies, I don't know what the status is on their release of public release of their involvement.
But if I can ask them, so the Multicore, the Avionics working group, do they have organized meetings, and are people
Yes.
not part of their founding members ever invited to those meetings? Just trying to figure out.
There are many more. There's many more companies involved than what's listed here as the founding members. Like I said, I was involved for years from its inception. There are specific rules set up for inclusion into this group that was worked out between the rest of the people in the group and the silicon vendors, because the intent is that through this organization, detailed design information is shared under NDA, and it allows the avionics companies to be able to understand the architectures, know the problems, where they might exist, and to know what they have to design around those devices
Thank you very much
to be able to
for
use
that.
it.
Okay.
But it is through this organization that data that allows the avionics companies from being able to go through the certification process is emerging. Next 3 slides, I'm not going to spend really much time on this. I've thrown these in here because, and I don't know what, it looks like I'm about out of time, but the fact is that there's an increasing desire or an increasing need to support security within avionics systems. Safety and security are 2 different things, but there are several common elements used to address the concerns of both safety and security. The hope is, and the desire is, that we leverage a common set of goals for both, so that we can develop systems that then can splitter off and then fill in the gaps to take care of safety, take care of security, and both safety and security where that is necessary. And I'm not going to go over this slide. It'll be in the slide deck. You can read through that. That's just a little bit more information on security. This is a summary. Basically, what I just stated, safety and security have a lot of common criteria: separation, data isolation, data integrity. There are evaluations from the COTS vendor that we can use for both safety and security evaluations. And the biggest intent is to understand what the common areas are so that we can do reuse between the 2. So now, current state and what future considerations are for Multicore within the avionics industry. Both FAA and EASA have released their guidance on what they expect to be able to certify a system with multi-core processors. Part of that guidance tells you things like turn off multi-threading. They don't want to see that. Maybe that'll change in the future. Within the industry, there have been some variants of multi-core that have been certified. There's been heterogeneous multi-core devices. There is at least one that I know of that is certified to, if you know what DAL A is, Design Assurance Level A. Heterogeneous processors is more than one processor, but they're not the same processor. So you get rid of a lot of the problems that you would have associated with having the same processor when you have a heterogeneous processing environment. Homogeneous processors, for instance, the P4080, that is 8 PowerPC cores. There have been instances of a single core being active and that going through certification processes. That doesn't really take advantage of multi-core, but it's the hope is that later that will be able to be certified as using more than one core. As I mentioned, multi-threading is almost always disabled, so that you avoid those issues. And there is work currently going on within more than one company for certification of applications within the civil and military arena for multi-core applications. Again, with the multi-core processing for avionics applications, the most common device currently in use is PowerPC. That is because the other major processing vendor got out of the military and aerospace field in the 90s, and although they wish to get back in and are making strides towards that, there's still a lot that has to happen before that's going to take place. But because of the reliance that we will go forward with having on ISO 26262 and the work going on in the automotive industry, these other companies that provide input to automotive will hopefully be able to be leveraged for avionics. We have to understand what gaps there are between 26262 and DO 254 and DO 178, etc. And we have to fill those gaps. But whereas most of those vendors don't want to come to the avionics guys because we don't sell that many, they will spend more time with the automotive guys, and so that's where we want to try to leverage that. And there, with this recent consolidation of silicon vendors, we don't know what the history of PowerPC is. There may not be a new PowerPC developed in the future. At least the core architecture. The most recent one that's out there is a few years old, and all the work currently is going into other processing families, which are being targeted more towards automotive. So we have to, as an industry, look at leveraging what's going on in automotive and perhaps other industries and try to leverage that to help us to find processors that we can use in the future. But we do have the power architecture that has been there for a while for us, and we have guarantees from the existing company, as long as that doesn't change because of the consolidation, where they will provide that for 15 years. So it's not like we have to change tomorrow, but we have to be ready to change when that happens. So here are the other industries that we're looking at to see where we can leverage what's being done for their safety applications. Avionics, of course, those are the three main standards that we have to adhere to. Automotives, the main one is the 26262, a couple of MIL requirements, and then several others from other industries that may be able to be used. But again, the automotive is the one that is the highest quantity and the most likely to be able to be used to augment the avionics industry. You can look at these. These were comparisons done. This one in a DOT publication, looking at the different cross-domain safety requirements. So what the differences are and where they overlap. And this one, which was done in a AutoSAR or a safe car. I think this might have been under AutoSAR. A report that was done a few years back shows the certification levels under these different safety specs. They don't all line up. They all have some differences, but we are trying to, as an industry, understand the commonality between them so that we can leverage what comes out of the other industries. And just closing remarks, I've kind of gone over each of these, so I don't think I need to really repeat them. I think I'm over time anyway, and that's the end.
That's all right. Well, thank you very much, Greg. And since we're running over time, we probably have time only for one quick question, and then we have a nice space carved out at the end of the schedule for a more in-depth discussion. Can somebody please do that?
I noticed you didn't say anything about any real-time operating systems people being interacting in face. Is that the case? But not really.
Interacting with face, did you say?
Not with face.
Oh.
I'm sorry.
Oh, MCFA.
I always get the acronyms wrong. Somebody
Yeah, face is a very different thing, and yes, the operating system guys are involved with face. Within MCFA, that was between the avionics guys and the silicon vendors, but the operating system guys were brought in, and they.
Because it seems like you need them.
Yeah. They needed to be there to explain how they were supporting the architectures that we were discussing.
Can you comment on some recent public press releases about Northrop Grumman says they're going to put Multicore in some utility helicopter, and the Raytheon's got an award to do Multicore for the F-16? Can you make any judgments on the validity or how far along you think those guys are?
I'm not going to make comments on another company's activities. I will say that yes, we have multi-core processors in military applications that are fielded. But in this this presentation, concentrating on civil certification and trying to get through FAA, EASA, and the other civil certification authorities. You can do things within the military environment that you won't be allowed to do within civil certs. But saying that, most military applications are requiring that you have a path to civil cert. So yes, we fielded multi-core, full use multi-core devices for other military applications.
Thank you very much.
Yep. Thanks.
Thanks again.